Okay, in section 1 of chapter 1, we're going to start reviewing some of our former topics. This first one is going to be on functions. Now, if you recall, a function is going to be a relation in which each x to 1y. So for each x, there's going to be one y value for that x. So a couple examples. One thing you could do is a mapping. So here's a mapping where you have some x values on the left. So these are my input or my x values, and then my y values there. And you can see on the function, each x goes to 1y. So negative 3 goes to negative 3. Negative 2 goes to negative 6. Negative 1 goes to 0. All these are a function because each x goes to 1y. Now, they can all go to the same y and still be a function. So another example of a function could be something like 2, 1, 3. And then if I just had a single number 5 there, and then all the x's went to that y, that is still a function because each x goes to 1y. It doesn't have to be a unique one. The second mapping is not a function because if you look at x and y, negative 3 goes to negative 6, that's fine. Negative 2 goes to negative 1. The problem here is 1, because 1 goes to 0 and 1 goes to 15. So you have two y values for a single x value. That makes it not a function. Let's look at this other example. This is a relation where we have some ordered pairs. In this case, I have 5 ordered pairs. I can plot them if I want. Negative 2, 1 is right here. Negative 2, 3 is right here. 0, negative 3 is right here. 1, 4 would be here. And 3, 1 would be here. So here are my points, but really what I'm trying to figure out is each x go to only one y? And the answer is no. This is not a function. Now, where this is not a function, where it kind of loses its ability is right here with these 2 points. Because you've got negative 2 going to 1 and going to 3. So that makes it not a function. So if you have that repeated x value with different y values, that's going to automatically make it a non-function. Another way to look at this one, if you remember from algebra, we had what was called the vertical line test. So a vertical line test said that every function will get intercepted by a vertical line at most once. So if I look at a vertical line here, you see it hits 2 of the points. So that also makes it a non-function. So the vertical line test will say any vertical line will hit a graph or intersect a graph at most once. So in this case, this one is not a function. So if you ever have points, you can certainly graph it. If you had a full graph, you can certainly use the vertical line test to determine whether it was a graph or a function. Another thing we'll use a lot in calc is the idea of a function notation. Now, function notation, as we've seen it before, is when you have the f in the parenthesis x. We typically call this f of x. And if you recall, really what this is this is just going to be shorthand for the functional value, for the value of the function at a given x value. Now, there's lots of things we said about function notation. We can also say it's pretty much the y value if you're given an x value. So if you have a relation with x and y ordered pairs, the y value is the function notation for a given x. So here's an example. We're trying to find some values and some really specific ones that we'll use in calculus a lot this year. So we're given a function, 2x squared minus 4x plus 3. So we're looking for f of 1, f of radical 3, f of a squared, and f of a plus h. Especially the last one is a very important one because we'll use that a lot when we find what's called a derivative. So what we're trying to do is we're trying to find the functional value for an x of 1. So the functional value for an x of 1, we know x is 1 in this, so really all we have to do is we have to replace all the x's with 1. So 2 times 1 squared minus 4 times 1 plus 3. And then I can just evaluate that. So that's 2, because 1 squared is 1, minus 4 plus 3. 2 minus 4 is negative 2, plus 3 is 1. So I know that f of 1 equals 1. So that also means on my graph, I know 1, 1 is on my graph. So the second one is square root of 3. So same idea, I'll plug it in for x. So I have 2 times the square root of 3 squared minus 4 times the square root of 3 plus 3. So the square root of 3 squared is just 3, so that's 2 times 3 minus 4 radical 3 plus 3. So 2 times 3 is 6 minus 4 radical 3 plus 3. Now remember, when you add radicals together, you have to have the same radicand, so I really can't do anything except for add the 6 and the 3 together, which is 9 minus 4 radical 3. So f of radical 3 is 9 minus 4 radical 3. So on my ordered pair, if I were going to do this on a graph, I would get radical 3 for the x and 9 minus 4 radical 3 for the y. So now we have the function value of different variables, and we use these quite a bit. So this first one is f of a squared. So what I'll do is I'm going to replace a squared with for all the x's. So I'll get 2 times a squared squared minus 4a squared plus 3. Now, not a lot I can do except for in this term, I can do a squared squared is going to be 2a to the 4th minus 4a squared plus 3. And that's all I can do because they're different exponents. I can't combine them, so that is going to be my f of a squared. Very, very common when you plug a variable in to a function notation, you get a variable expression out. Finally, let's look at f of a plus h. Now this one, very, very common. So I will again replace, in this case, a plus h for all the x's. So I get it 2a plus h squared minus 4a plus h plus 3. I just want to stop here for a second. Notice when I put these in, I made sure they were all in parentheses. If it's a single variable, it's not as big a deal, but it's always a good idea to put parentheses, especially if you're plugging in binomial things with two inputs. So what I'll do first is I'll square this, and squaring a plus h is not quite as simple as squaring each one. When you square a binomial, remember we will write it twice. So it will be 2a plus h, a plus h. And so I have to FOIL that one in my next step. Here I can distribute the negative 4, so minus 4a minus 4h plus 3. So in this one I will FOIL, so I'll get a squared plus ah, so that's first, outer. I get another ah there, and then last I get h squared minus 4a minus 4h plus 3. So I notice I can add these two together. So I get 2a squared plus 2ah plus h squared minus 4a minus 4h plus 3. And then I will distribute the 2. So 2a squared plus 4ah plus 2h squared minus 4a minus 4h plus 3. And if I look here through every term, I don't honestly see anything that would combine. So this is my f of a plus h. The biggest thing there is to make sure when you square a binomial, when you square two things added or subtracted together, you make sure you write them twice in FOIL. That's one of the big fundamental errors people will make in upper level math. So be very, very careful of that. Some other parts of function we'll be talking about are things that you should have done in pre-calc, talking about parts of a graph and parts of a function, namely the domain, the range, the zeros, and the y-intercept. So if you remember domain are the possible x values for a function. So lots of functions have values that they cannot be. If you remember, logarithmic functions have to be only positive. Square roots cannot be negative. Things that are fractions cannot have 0 in the bottom. So there are always things that you have to exclude when you're thinking about domains. The range is going to be possible y values. So what are the possible functional values for a function? Thirdly, we have zeros. Zeros are going to be x values when plugged in give 0. So you plug a number into a function and it gives you 0. If you recall, zeros are always at x-intercept. So if you have an x-intercept on your graph, that is also a 0 of the function. The only exception to that would be is if you have complex, if you have imaginary zeros, then those don't have x-intercepts. But quite honestly, in calculus, we do not deal with imaginary numbers very much. So we will just say for us, our zeros are going to be at x-intercepts. The final thing we'll look for in a lot of functions is a y-intercept. Now, a y-intercept is obviously where the graph crosses the y-axis. And this is always at f of 0. So you plug in 0 for your x value, and that is going to give you your y-intercept. That's always going to be where your y-intercept is, no matter what kind of function you have. Zeros now. So let's look at some examples of finding some of those terms we just talked about. We'll talk about finding the domain, the range, the zeros, the y-intercept of the function. And graphs are always very helpful in doing this. Remember, you have Desmos, you have graphing utilities. You can always use those. Those are always going to be available to you on tests and quizzes and things like that. So don't be afraid to graph these things when you're looking, especially for things like the range. That can be very difficult to find without a graphing utility. So this first one says f of x equal x plus 2 squared minus 4. So this is a quadratic function. Now, if I want to graph it, I certainly can. So if I graph it on my Desmos or whatever you want to do, it's going to have a vertex at -2, -4, and it is going to point up. So it looks something like this. Okay. Now, if we think about it, for the domain, it's a quadratic, it's a polynomial function, so there are really no real exceptions to this. The big exceptions to domain are square roots, they're division of polynomials, and they're any kind of logarithmic or some of the trig functions have domain restrictions. But for this one, there's nothing really there. So the domain is going to be all real numbers, or in our interval notation, -infinity to infinity. So, and if you look at the graph, if you pick any x value, it would be a point on the graph. If I pick x of 5, well, somewhere up here on the right is a point that has an x of 5. I don't really know what the y value is, but it's some y value. Now range, if I think of the range of this, the lowest y value I can get to is -4. I cannot get below -4 because this point has my smallest y value. So my range is -4. And remember, in interval notation, if you have a bracket, that means included. And if you have a parenthesis, it means not included. So in general, for domain and range, you can use brackets for numbers and parentheses for the infinities. So we have -4, and then the highest, the y values will keep increasing. So the y value, the biggest, is going to be infinity. So domain is -infinity to infinity, and the range is -4 to infinity. Now for zeros, we're trying to figure out where this function is 0. So the easiest way to do this is I will just take my function and I will set it equal to 0. So I'll take x plus 2 squared
minus 4, and I'll set it equal to 0. And then I'll try to solve it. So there's lots of ways to do this. What I'll do is I'll go ahead and add 4 to both sides. So I have x plus 2 squared equals 4. I now have a square, so the opposite of square is square root. So that's going to give me x plus 2. And the square root of 4, since I took the square root of 4, it's going to be plus or minus 2. When you take the square root, you always have to add the plus minus. Subtract 2, I get x equals negative 2 plus or minus 2. So if I do negative 2 plus 2, that's going to give me a 0. And if I do negative 2 minus 2, that's going to give me negative 4. So my zeros, which are always the hardest ones to find, are going to be x equals 0 and negative 4. So if I were to plug those into this function, I would get 0. You can check that. Plug in 0, plug in negative 4, you would get 0. Finally, I have to do the y-intercept. The y-intercept, remember, is always f of 0. So I'll just go ahead and plug 0 in for the x's. So f of 0 is going to be 0 plus 2 squared minus 4, which is 0. So the y-intercept is 0, 0. So my graph is a little off. Remember, it was just a sketch. I didn't really graph it on Desmos, so it really should cross there. I know my other 0 is negative 4, which would be there. You have a 0, 0, and a y-intercept at 0. So again, graphing it is a real nice tool. You really could have probably figured out this 0 and negative 4 from the graph versus actually doing the algebra. Okay, let's go ahead and look at another function. This is a square root. And remember, we said square root is one of those functions that does have some problems. Square roots must be always not negative, so it has to be greater than or equal to 0. So I could graph it again if I'd like to. Or I could try to do the algebra by hand first, doesn't really matter. Maybe this one I'll do the algebra by hand. So I'm doing the domain. I'm trying to figure out what x values I would use. Well, really, I want the stuff inside the square root to be positive. So I could just set 2x plus 4 greater than or equal to 0. So if I solve that, I'll subtract 4, and I'll divide by 2, so x is greater than or equal to negative 2. So the domain is all values bigger than or equal to negative 2. So negative 2 is my smallest, and it gets as big as you want, so we'll go to infinity. Now range is going to be pretty tricky, so that's where the graph might come in handy. If I look at the graph of this square root, it should start somewhere here at negative 2 and negative 3, and kind of goes off in this direction somehow. So the range, you can see the smallest, the lowest value is going to be at that negative 3 point. So we'll go negative 3 to infinity. So again, the way I have it, it looks like it's somewhere between negative 1 and 0. That may be true, that may not be true, because I just kind of sketched it. So if I wanted to find the zeros exactly, I'll set it equal to 0. So I get square root of 2x plus 4 minus 3. I'll add 3 to both sides, so I get 3 equals square root 2x plus 4. I'll go ahead and square both sides. That'll give me 9 equal to 2x plus 4. I'll subtract 4 from both sides, which will give me 5 equal 2x. And then dividing by 2, x will equal 5 over 2. So my only 0 in this case is x equal 5 over 2, or 2.5. So again, my 0 is over here, so it probably looks something more like this. But again, we're improving our graph the more information we get. Unless you want to graph it on the graphing calculator, then it should be pretty precise. And then we can go for y-intercept. Now, our new graph, this is our second more refined graph. Looks like the y-intercept is somewhere in the negative range between 0 and negative 3. So let's go ahead and check that. Because remember, that's going to be f of 0. Or in this case, it would be g of 0, since we're doing the function g. It doesn't really matter. So g of 0 is going to be the square root of 2 times 0 plus 4 minus 3. So that's the square root of 4 minus 3. So that's 2 minus 3, so that's negative 1. And you'll notice our second graph with our more information, it looks almost exactly like it was. 0, negative 1 for our y-intercept. So the more information you get, the better graph you can get. A lot of calculus will be trying to find these properties of the graphs that you quite honestly can verify quite easily with a graphing utility. When we get to chapter 4 of the book, a lot of stuff about graph theory. Finally, let's look at this one, which is a rational function where we have a top and bottom. Now, the big thing with a fractional thing, if you recall, you can never have the denominator equal to 0. So we don't want the bottom equal to 0 here. So we don't want x plus 3 to equal 0. We do not want that to be 0. That would be a problem. So just subtracting 3, I know that x can't be negative 3. So for my domain, it's all real numbers except negative 3. So it could be any negative number all the way up to negative 3, but then I'm going to take a break. So I have my parenthesis, union, negative 3 to infinity. So really, this is saying all the numbers from negative infinity up until you get to negative 3, take a little break, start at negative 3 again, and go all the way to infinity. If you had multiple ones, you might have to do multiple exceptions, but that is the idea. Now, the range of these are very, very difficult if you don't have a graph of it. So I'm just going to kind of sketch a quick graph of it. At negative 3, you'll see it has a vertical asymptote. And these rational functions, all the values that are undefined make vertical asymptotes. And so what this one looks like is something like this, where it kind of approaches this way and then kind of approaches this way. So it's these kind of two things. So what you'll notice is it seems to flatten out at 0, but it never really equals 0. It just kind of keeps flattening out. So the range is basically everything except 0, because you can see at 0, it's kind of a gap. It doesn't ever touch 0. So we'll say negative infinity to 0, union 0 to infinity. I will say most certainly domain much more important in calculus and math in general than range, but from a graph, not too hard to get range. Now, as far as zeros, you can actually see from our graph, zeros would be x-intercepts where this crosses the x-axis. Well, it never does. We said this is a horizontal asymptote on both sides, so it never touches the x-axis. So there is no 0. Now, for y-intercept, we'll do h of 0, so we'll just plug in 0 for x. So we get 4 over 0 plus 3, which is 4/3. So 0 4/3 is our y-intercept, and that kind of makes sense in this sketch of my graph. So it's some value kind of above 0. All right, the final thing we're going to look at in section 1 is the composition of functions. Now, the composition of functions is when you take a function of a function value. So we're going to take one function of some x value, and then we're going to take that value and plug it into another function. We typically denote this as f of x, f of g of x, or g of f of x. But both of these just equal the f of the g of x. So I take the g function first for some x and then plug it into the f function. Or in this case, it would be g of f of x. Whatever function comes second is the function that we will plug in. Now, when you do a domain of a composition function, we have to do, once we do the composition, we have to look for what domain there is, but there's also one additional step. So we can say the domain of f of g of x is all reals except those that make our final answer f of g of x and g of x undefined. So we have to not only look at our final answer, f of g of x, we have to also look at the function that we plugged in, because you can't take an undefined value and plug it in. So in practice, it's really quite simple, but that is the definition. So let's look at this first example of composition. It says we have f of x equal 2x squared plus x minus 3, and g of x equal negative 4x plus 5. And I want to find f of g of x. So remember, f of g of x is f of g of x. So I'm going to plug the g function into f. So everywhere I see an x in the f function, I'm going to plug that g function in. So in doing so, I'm going to get 2 negative 4x plus 5 squared plus negative 4x plus 5 minus 3. And then I'll have to simplify this. So just like before, remember when you square a binomial, we're going to write it twice. So negative 4x plus 5, negative 4x plus 5. Nothing to distribute in this one, so this will just be negative 4x plus 2, because I can put the 5 and the negative 3 together. If I FOIL these two, I'll get 16x squared. On the outer, I get minus 20. On the inner, I get minus 20, so that's minus 40x plus 25 minus 4x plus 2. I'll distribute the 2, so I get 32x squared minus 80x plus 50 minus 4x plus 2. And then just by combining terms, I've got the 50 in the 2 and the 2x terms. My composition is going to be 32x squared minus 84x plus 52. Now, we also wanted to look at the domain. So the domain, first of all, we want to look at our composition. At the end, this is just a quadratic. I can put any x in I want. There's no exceptions there. I also want to look at the function I plugged in up here, the negative 4x plus 5. Is there any x that would make that undefined? Well, there's not. So the domain is all reals. Remember, the things you want to look at for domain restrictions are fractions, square roots, logs, trig functions, things like that. All right, let's look at this second one. Now, this one might have a little more involved domain I can see because I have a square root and a rational function. So it says I want to find the composition f of g of x, so f of g of x. So I'm going to plug the g function into f. So when I do this, f of g of x is going to be big square root 3 over x minus 7 minus 3. Now, if I was going to simplify this, what I would do is I would get common denominators. So I'd multiply top and bottom by x minus 7. So that's going to give me square root of 3 minus 3x plus 21 on the top, because I'm distributing this negative 3, all over x minus 7. That is going to be the square root of 24 minus 3x over x minus 7. So hopefully this isn't too bad. We do a lot of compositions in calculus, especially when we start doing integration. So a good skill to practice and review. If you do have any questions, please let me know. We can go over your questions.